In this session, we'll be looking at the decision making we can do through hypothesis testing, which is really the key takeaway for this class. You know, what we're really trying to understand is how unusual are the observations that we have in a sample when compared to what we would expect in the population. So in other words, we're trying to figure out how weird things really are and whether we can make some kind of decision by quantifying it. We want to be able to frame some hypotheses for testing those weirdness that we are observing. We're going to do that through significance tests, and then we want to be able to compare also means, proportions, and variances for weirdness, and I'll show you a method to do that. Strange world, isn't it? Author Stephenie Meyer, famous for some recent novels related to vampires and other fantastical things, so she should know. Framing hypotheses, this is a claim about a population parameter, not a sample statistic. So we're getting a sample statistic in our samples, but what we're trying to understand is something bigger about the population. And really that's what the statistical tests are doing. That's what the central limit theorem is so important for us to do in inferential statistics. The null hypothesis is assumed to be true. And an alternative hypothesis has to be crafted in order to test the assumptions or challenge the assumptions of the null hypothesis. So for example, a new Salesforce bonus plan is developed in an attempt to increase sales. The null hypothesis would be that under the new bonus plan, there's completely equivalent, because that's the null hypothesis to what we're doing right now. The alternative hypothesis says, no, sales are going to be significantly higher than in the current bonus plan. And then we'll use the statistics to figure out what that means. The framing of the hypothesis is very important, and I'm going to show you 3 different ways that are commonly done for us to look at this in hypothesis testing. The hypotheses for the null is always going to be that things are equivalent, and you'll see that no matter how we frame it, the null hypothesis will always have some kind of an equivalence, and the alternative hypothesis will not. In general, we're trying to test to see if the mean of a population based on the information we have on our sample, is unusual or different. So continuing with a bonus, here's how we would look at one example, the way that it was framed in the prior slide. Under the current sales plan, the average sales per day are 1,000, and the new sales plan is supposed to increase that. So the null hypothesis would be, well, there's just going to be no difference. So the null hypothesis is the new sales plan is either underperforming the current level or equivalent to it. So if any of these results show up in our sample when we look and test, we'll know that we're really in the null hypothesis situation. We'd have to be able to see something like this, where in some statistically significant way, the value of sales have increased over 1,000. That's how we would then be able to accept that we're the alternative hypothesis in this case, that the new sales plan, the new sales bonus plan is improving or increasing sales. Now, there's another alternative, and no one wants to really think about this, but perhaps under the current plan, the null hypothesis is that it's going to be equivalent or stay the same, but what if the new sales plan fails? If the new sales plan fails, however unlikely it might be in our minds, because that's why we've designed it, it could be that sales go down. In this case, we would still say that we would reject the null hypothesis if this showed up in our sample and we could prove it using statistics, basically collect enough evidence to suggest is a better way of saying that, don't really prove it. We would be able to look to see if the new sales plan has caused things to go down or decrease. So this is the other end of the spectrum. And you might recall the central limit theorem with the normal curve. This is why those tails and the percentage of observations in the tails are important. And then we could put it all together in a two-tailed test rather than just looking at one side of things. We could just say, well, we don't know what's going to happen. Under the current sales plan, the average sales are 1,000 per day, but we just know that the new sales plan is going to change that. So the key operative word here is change. Notice I didn't say that it was going to improve sales or decrease sales, increase sales or decrease sales. I just said it's going to change sales. That's a flag that we're really just looking for a change between some sample that we have and a population. In that case, we're just going to test to see that it's not equivalent to the average that we would expect, which is $1,000. But the null hypothesis is that there's no change. This is the current, so null hypothesis is it stays the same. Alternative hypothesis is that something other than $1,000 at some significant level. So putting those together, what we see are the three different ways that we can frame hypotheses, and you'll notice all the null hypotheses have some kind of equivalence. They might be less than or greater than, but there's still an equivalence, and certainly the two-tailed test has equivalence with no greater than or less than. And then all the alternative hypotheses don't have an equivalence. So that's one way to know that you're dealing with an alternative or a null hypothesis. This is a way that it may look visually if you were to sort of plot this out. Here's my current sales plan. This is all the sales that I get in a day with an average, as we read, based on a sample, would be 1,000 maybe that we're trying to measure. Well, in this picture I actually have it being measured a little bit less than 1,000, but nevertheless, we know that we expect the current sales plan to produce about 1,000 in sales, and maybe our sample is a little bit lower, but the real point of the picture are really these other two distributions that we see. It could be that the new sales plan increases things, and if it increases it to a significant level, then we can reject the null hypothesis that we're really dealing with this kind of distribution of sales anymore. We're in a new world with sales that are significantly higher, representing a new population. You can see here, this could be a sample that might drive that decision because it's so high. It's so high and so far away from the original population I thought I was in that we would definitely say, yes, if this showed up, this would be so unusual, so rare, so weird that we must conclude that the new sales plan is really driving new heights of sales. And then here, this is a little bit less clear, but perhaps this shows up. Maybe sales have actually decreased. And so in this case, they definitely would have decreased a lot. This would be the sample, a third sample that we just did, and maybe this showed up in a sample. And this would definitely say it's pummeled sales. It's significantly less than where they were in the current sales plan. So putting that together in words, a different sampling distribution means that are not close together. When the null hypothesis is false, both of these situations are showing us that the null hypothesis is probably false. A little bit less clear with this because there is an overlap still. You can see here more so than in this world with the original sales plan. But still, the means here are significantly different. You can see from the original sales plan. And so this would definitely give me a sense that the null hypothesis can be rejected. So we would reject the null hypothesis and say there's support for the alternative hypothesis. The new sales plan is significantly increasing in this case or decreasing sales. Now compare this situation to this next picture here. If all of the means are clustered together around the original mean value of, in this case it was $1,000, there's really no difference between any of these plans. Yeah, sure, things have shifted a little bit higher or lower, but in this case we cannot reject the null hypothesis because the pictures just don't really allow us to when we're comparing the means. Based on our samples, we don't have evidence that we're operating outside of the original population that we were sampling to begin with. And in this case, we cannot support the alternative hypothesis. That's how you would interpret that. Now, there's a matter of significance level. I've already talked in, I think, a prior session about how we look at the significance level at a 0.05 level with a two-tailed test. It leaves a little bit of a proportion of the values in the z-score normal curve to be sort of extreme. And we were using a z-score of 1.96 to measure that. And the interpretation of that is, again, in theory, if you kept sampling over and over from the population, this would give me 95% confidence that all the values expected would be in this boundary of 95%. And that's why the 0.05 level of significance is often used so often. If my sales plan results in a z-score that's outside of that boundary, then, only then, can I reject the null hypothesis. That would be the case where sales, in this case, may be significantly different at either end. So again, this picture that I'm trying to verbally describe is that in theory, if I kept taking a sample over and over, and I'm likely to just draw from the values that give me that 95% confidence that I'm still around my population mean of, say, really maybe the population is $1,000 in sales. There's going to be some samples that I get where I only maybe sell $800 a day in that sample. Other times, maybe I sell $1,200 a day in the sample. But I'd have to really be out there, having like practically no sales, or maybe I sell 10,000. In this case, I'm trying to represent maybe my sales plan is really effective and it's helped me drive sales, and I'm up here in the upper tail. If that showed up, you can see it's pretty unlikely that that observation in that sample, which is supposed to represent the population, in fact it does in inferential statistics, this observation is so weird that I'm really no longer part of the original distribution of sales. It's quite unusual. It's exceeded 1.96 z-score. I don't know what that is, but it's really high. It's probably over 2, maybe over 3. So in that case, I'm looking at a very extreme situation. I want to illustrate the other situation here where if I wanted to just predict that my sales plan was going to improve sales, I could do what's called a one-tail test. You'll notice something really important here has happened. Now I'm no longer looking at the two-tail test. I get to group this entire area of weirdness, if you will, of being an extreme value, all on one tail. I'm putting all 95% of the values down below this z-score, whereas before I had to split it up. That's helpful to me because if you notice, I only need an observation out of a sample now to be 1.645 z-scores above the mean. Whereas here I needed a z-score at the extreme of 1.96. It's much harder to get a z-score at that extreme. So if you notice here, a one-tail test allows me to put all of the detection of weirdness, which would maybe give me a sense that I'm looking at a different population, all into one tail, which actually lowers the z-score because I got all 5% up in one area. So this is known as a one-tail test. It makes it a little easier actually for me to reject the null hypothesis and find a trend. So this would be a picture of what I just described. Maybe this is the original sales plan without the bonus that I put in here, but I've observed this, and now this is really representing a whole new world of potential sales that we could drive. Today I'm got a value that's right here, super extreme on this original normal curve, but maybe on a new population. So other examples that could be like that might be a little bit easier to think about. If you were to imagine looking at the heights of all the professional basketball players versus non-professional basketball players, I bet it would look something like this. This is the general population of non-professional basketball player heights, but the professional basketball players have a huge range of heights, and it's a whole new population. It's still a normal curve. It's just a different population than the population of non-NBA players. Patients that take an effective therapy versus control group. So here's my control group, but taking my therapy, I'm in a new population of patients who are well. All of these patients originally were ill. Maybe that's what the control group that did not get my therapy, but I took a sample of them, and now I've actually moved patients up into a wellness curve, which indicates they're in a different population altogether. How about superpowers that are present in the Justice League versus everybody else? So here's everybody else, but we got the Justice League here with Superman and Batman and Robin, and they would definitely be in another population altogether. We don't have any superpowers down here. So p-value is a way of looking at the probability. It's related to the confidence interval idea, but now we're going to calculate a statistics that is called the alpha, which helps us interpret it easier than confidence interval, or in addition to confidence interval. The p-value that's less than or equal to some level of significance, which we'll call alpha, is our test statistic, and it basically relates to the region that we were looking at on the prior curves. If we have some kind of observation that's in that range of weird in a good way, could be that we've observed something unusual, then we can reject the null hypothesis. If your p-value is less than the difference you have tested for, we'd say that that's significantly different than the null hypothesis. There is a statistical evidence supporting significant difference at that level of confidence. So for example, most of the time we're looking at p less than 0.05 before we get really excited about things. There'll be some examples that are exceptions, but most of the time we want to see significance at level p 0.05 or less. And that would mean that there's something unusual going on. Here are some guidelines in terms of ranges of significance. P-values that are less than 0.01 are very, very strong, because that means that it's very unlikely to occur. I think I have some interpretation of that coming up. Between this range would be strong evidence, moderate evidence, and then insignificant evidence that we shouldn't really reject the null hypothesis. Anything that's above 0.1 is very difficult for us to interpret that we're looking at a new population, if you will, from our sample. So here's a way to interpret that. If we're looking at p-values, alpha values of 0.10, whether it's 1 or 2-tailed, rejecting the null hypothesis at the 0.10 level indicates that there's less than a 10 in 100 chance, or a 10% chance, in other words, of observing a result that's in that range, if the null hypothesis were true. So if the null hypothesis were true, I'm likely to see this kind of a value or higher, but I'm seeing something that's at this value or lower, so I can reject the null hypothesis. The null hypothesis must be false. Going to the next level, 0.05, this is the most common for the social sciences. A lot of business still looked at this. Rejecting the null hypothesis at the 0.05 level indicates that there is less than a 5 in 100 chance of observing result that's in that range if the null hypothesis were true. And finally, at the 0.01 level, rejecting the null hypothesis at that level indicates that there's less than 1 in 100 chance. So this is one way to understand the relationship between the alpha level and effectively a percentage of likelihood that we're rejecting the null hypothesis appropriately when they show up. Now, we have to be concerned when this is a probabilistic exercise. So, this might be review for some of you, but you may recall that we could reject the null hypothesis falsely. So if we've done that, we have a false positive. We've rejected the null hypothesis, meaning we've accepted the alternative hypothesis, and we've claimed that there's a difference when there is none. That's a type 1 error. Now, the opposite could also be true. We could accept the null hypothesis when it's false. In other words, we miss something that we should have seen. That's to be a false negative. We want to avoid both of these situations, and they're going to be related to the amount of error that we're accepting in our data. Here's the example with the sales plan that we talked about earlier. If in reality the population statistics have shown that sales have improved, it's really made things go up. And we say from our tests that they have gone up. This is goodness. That's positive. Also, we want to, of course, if sales have not improved and our statistics say they haven't improved, then those are the true situations where either it's positively and we've identified it, or negatively and we rejected it. We've retained the null hypothesis here. The problem is on these corners. So sales really did improve, but we didn't detect it. Our statistics said, nope, retain the null hypothesis. Well, that's a false negative. We've missed that opportunity to say, hey, sales have really improved. We should be doing those things. The worst situation most of the time are these type 1 errors. It does depend on what you're measuring, but if sales have not improved and we said that they are, that could lead us down the path, especially in business, of implementing a program that's not really effective. So this could be very costly. A type 1 error is a false positive. We believe and have shown erroneously that the sales bonus plan has improved sales, but in fact, they have not. That's a type 1 error. Now, there's 3 tests that we'll refer to, again, using SPSS where we can. We've been looking at a lot of z-tests. It's fairly easy to calculate these by hand. We can do some of them in SPSS. It usually assumes that we know a population variance, and we don't always know a population variance. So it's important to understand these other tests that we're going to be doing. A t-test is which is looking for the significance of difference, usually between 2 groups or between 2 means. We'll be utilizing a t-test. And the chi-square test for looking at significant differences between proportions or variances of 2 or more groups. I'm going to demonstrate these for you. Let's look first at the chi-square test. Here we have a Buyer's Digest, which is like a consumer group rating thermostats. This is similar to that situation that we had earlier. They take 10 thermostats and they want to evaluate how well they are maintaining a temperature in Fahrenheit. And so they took a sample of 10, and then this is the data that they got in Fahrenheit from those 10. And what we're looking for is these thermostats can't vary more than half a degree Fahrenheit between them for them to get a positive rating from this Buyer's Digest. And so using the 10 readings, let's conduct a hypothesis test at this level of significance or confidence, if you want to think of it that way, to determine whether they're in fact in an acceptable range. So we have a target here that the magazine has given us, a variance of a half a degree. Half a degree Fahrenheit is our variance for the population that they want to test for. And knowing that, we're able to start to plug some things into a null hypothesis and an alternative hypothesis. The null hypothesis is that the variance in these readings are going to be equal to that target, and so or less. So the null hypothesis is that there's no difference, and this is kind of goodness actually, because we really don't want these to be different. Quality to us is that these are measuring accurately across all the units, that these temperatures are within that range. The alternative hypothesis is that the variance in the temperature of the readings is greater than half a degree, greater than the variance that they gave us. And we can use the table of chi-square to look up these numbers. Again, I find a lot of similarity thinking about these like z-scores, but I'll show you how you can get them from a table. And we would need this information to do that. But conceptually, here's what's going on. We are trying to understand if, based on the information that we got, this variance was given to us in the population. We have a sample, and we can compute the sample's variance, which is going to come from those thermostats, and we can get a value that we need to be at or above, really it needs to be above, before we would reject the null hypothesis. Anything above this is unusual, and it means that the variance in those thermostats are too high. You see that? What we want is to stay in these acceptable ranges, and that's everything below it. Well, you could argue that the magazine should be testing for thermostats that are this low, but in this example, we're looking for things that are variances that are really high. And this would just be a very accurate thermostat down in here with very low variability, so that would be a good thing. Now, this is the way that we would plug that in. In this case, we actually finish doing the calculation, and our sample's chi-square is 12.6. Again, you could think about this like a z-score. This could be an obtained z-score, and I'm showing you how similarly the thinking is to the normal distribution with the z-scores that we did before. This is the chi-square level. Anything above this we have to reject, and anything below this is going to be our sample's variance, and it looks like we're going to be okay here. We fail to reject the null hypothesis. The exact p-value is this, and in this case, rejecting the null hypothesis was goodness, that the sample was within an acceptable range. Because the chi-square is less than this, we cannot reject the null. The sample variances that we got are insufficient to conclude that the temperature variance for this thermostat is unacceptable. The thermostats are working because we are effectively below the limit. Because in this case, because they gave us the variance that we had to be at, which was half a degree, our null hypothesis was testing the entire time to see, are we at that or below it? And so we're in good shape here because we could retain the null hypothesis that there's no variance that's to worry about in our sample. I'll give you a second example. We can also use this thinking to compare two sets of thermostats against each other, and we can look at their variances. And so in this case, we have 10 thermostats now from two different manufacturers, Tempking and Thermalright. And we want to compare to see if the variances between these two samples are effectively equivalent. So our null hypothesis is that they have the same temperature variance. In the prior example, this null hypothesis was that they were equivalent to the variance that the magazine had selected. Now here, we're saying that they're not equal in the alternative hypothesis. So we're going to be testing this variance, which you don't have to do by hand. We'll be doing this in SPSS, but I'm showing you how the numbers would come out. And in this case, we cannot reject this because our statistics here were insufficient evidence to conclude that the population variances were different between the two brands. But what that means is that these two brands effectively are performing at the same level. They were equivalent to each other, and so they're really the same, and so we're not seeing a difference in performance. If we had rejected it, we would have known that one of these was performing different than the other, and we could go and look at their values and see where the variances might have been higher for one group of thermostats versus the other. Now, we need to also understand this concept of goodness of fit. Goodness of fit is a way of looking at proportions, probability distributions of proportions. A population will follow this multinomial distribution with a specific probability for each number of categories. I know that's a lot to think about, but I'll illustrate this in just a moment. The population does not follow this under the alternative hypothesis. In other words, there's going to be a difference here across the categories. Let's use an example to take a look at this. Finger Lake Homes manufactures some pre-manufactured homes. They have a colonial style, a log cabin, and a split level, and an A-frame. And we want to be able to help plan to determine if previous customers' purchases have some kind of preference across styles, because maybe we need to make more styles in one particular category. So here's the data that we have, 100 sales over the past 2 years, and so we've sold 30 colonials, 20 log, 35 split, and 15 A-frame. And what we're going to be looking for is to see, are the proportions sold equivalent? This should sound familiar. We've looked at some of these other kinds of tests when we were looking at other distributions in prior sessions. And in this case, the null hypothesis is that they're just all equal proportions across all of them is what's hypothesized. The alternative would be that there's some difference, that they are not equal. And so, you know, that's really what we're trying to understand before we can reject the null hypothesis. Now, again, we can use the tables. I'm not going to illustrate that here to figure out what these values are. We're going to have SPSS do that for us. But conceptually, what we're looking for is our sample of 10 that we have here, we can hit a level of chi-square that anything above this, we can reject the null hypothesis. That is going to tell us that there's some proportional difference between all the different homes that we have in our sample. If we retain the null hypothesis, or in the rejecting null hypothesis, the assumption is that there's no home preference style. Some homes are preferred more than others because we'll be in the alternative hypothesis. So, this is a test of independence. This is another type of illustration that we can do through a chi-square statistic rather than using a table, which we had done in a prior session. Here, we're looking at the difference between an independence of a row variable and a column variable. And the null hypothesis is that these are independent, and the alternative hypothesis is that they're not. So let's take a look at this example. This same home company is looking to understand if there's a relationship between price and style. The manager would like to determine if the price of the home and the style of the home are independent. The number of homes for them being sold are here, and you've already categorized them conveniently for us in terms of whether they sold for less than $200,000 or equal to or more than $200,000. And these are the number of sales that they had. By using this information, it might look familiar. It is the same kind of contingency table that we had looked at in a prior session. And we can sum up these values. This might look familiar to us. And at the time, we were using different methods to count things by hand, to put some values in. I think we also looked at some binomial distributions and things like that. But we can use the chi-square test for dependence to actually look at this as well. The null hypothesis is that the home price is independent from the style. Here, in the HA, alternative hypothesis, the price is not independent. We can do the math and use the chi-square test. Our sample's chi-square, it turns out to be 9.15, which is, again, in this reject region. So by rejecting the null hypothesis, we're saying there is some kind of relationship. There is some kind of dependence We reject the null hypothesis that price of home is independent from the style. The price of home is dependent on the style of home, which may not be surprising that the price might be maybe more or less for certain models. And to know exactly which ones, we'd have to do additional tests, but this is how the test of independence helps us do that. And we would use SPSS to do that for us or with us. So the takeaway for this session, we've used statistical inference here to determine something about an observed result that's rare or unusual on chance alone. And by that, we can make some decisions on whether we want to reject a null hypothesis and take an alternative hypothesis, or whether we're still at equivalence. It's helpful to frame null hypotheses with some kind of equivalency, typically, to see that we're expecting no change or no difference, and then we can reject the null hypothesis in support of the alternative hypothesis when those observations reach a certain standard, like a p less than 0.05. That would tell us that something unusual or rare is going on. And we also saw how z-scores and t-tests for testing the mean differences, and chi-square tests are good for proportions and variances. We can use the goodness of fit and the independence test with the chi-square test helping us out.